The world we see is not all there is. Beneath the surface of our everyday lives, a different reality operates. This is the quantum realm. It is a place of profound mystery, a place that challenges our deepest intuitions. Scientists venture into this realm. They return with tales that sound like fantasy. Yet these tales describe the very fabric of existence. Quantum physics was born in the early 20th century. It arose from puzzles that classical physics could not solve. Light behaved strangely. Atoms were not tiny billiard balls. Instead, they were fuzzy clouds of probability. Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, these were some of the pioneers. They unveiled a reality that was granular, not smooth. A reality built on discrete packets of energy called quanta. This was a revolution. A fundamental shift in our understanding of everything. This new physics is not just a theory for tiny particles, it underpins all of modern science. It explains how the sun shines, it is the basis for computers and lasers. It is essential for understanding chemistry and biology, yet despite its successes, its core concepts remain baffling. They speak of a reality that is fluid, uncertain, and deeply interconnected. One of the most unsettling ideas is superposition. It means a particle can be in many places at once, or it can possess many properties simultaneously. Think of an electron. It is not always here or there. Instead, it can be in a haze of possibilities, a cloud of potential locations. Only when we look, when we measure, does it choose a spot. This is not a limitation of our instruments. It seems to be the fundamental nature of the particle itself. Imagine a special quantum coin. Before it lands, it is not heads or tails, it is both at the same time. It exists in a superposition of states. This is not just a philosophical notion, it has real, measurable consequences. This ability for particles to exist in multiple states is key. It is what powers the dream of quantum computers, machines that could solve problems far beyond our current reach. By using these multiple states, they can perform many calculations at once. This idea of superposition is deeply challenging. It shatters our everyday experience. We see objects in definite places with definite properties. Then there is entanglement. Albert Einstein called it spooky action at a distance. It is perhaps the strangest quantum phenomenon of all. Imagine two particles. They interact and then fly off in opposite directions. They could be miles apart, or even light years apart. Quantum mechanics says these particles can remain connected, their fates intertwined. If you measure a property of one particle, you instantly know the property of the other. Instantly. Faster than light could travel between them. This connection is not like knowing two gloves are a pair. If you have one left glove, you know the other is right. That is simple classical information. Entanglement is different. The properties of the entangled particles are not fixed beforehand. They are genuinely undecided until a measurement is made. It is as if particle A knows what measurement was made on particle B, and it adjusts its state accordingly, instantaneously. This does not mean we can send messages faster than light, but it does suggest a deep, non-local connection. Entanglement forces us to rethink space and connection. Are distant objects truly separate, or can they share a single unified existence? The observer effect is another pillar of quantum weirdness. It states that the act of observing a quantum system changes it. Before observation, a particle might be in a superposition, a wave of possibilities. But the moment we try to measure it, to pin it down, the wave collapses. The particle chooses a definite state. It is as if reality waits for us to look before making up its mind. This is not simply about clumsy measurements disturbing things, it seems to be a fundamental feature of how reality works at this level. In the quantum world, the torch of observation is not passive, it actively participates in creating the reality it observes. This raises profound questions. What counts as an observer? Must it be a conscious being? Or can any interaction with another system, like a detector, cause this collapse? The observer effect challenges the classical ideal of an objective reality, a reality that exists out there, independent of us. Quantum mechanics suggests this picture is too simple. For scientists, these quantum concepts are not just intellectual puzzles. They are a source of deep conceptual struggle. Physicists are trained to think in terms of cause and effect, of predictable trajectories and definite properties. Quantum mechanics throws all this into disarray. It speaks in the language of probabilities, not certainties. It describes a world that behaves in ways that defy common sense. This can be profoundly unsettling, even for those who work with it daily. Imagine trying to describe a dream using the language of engineering blueprints. The tools are not quite right for the job. Similarly, our classical intuition, honed by experience in the macroscopic world, fails us in the quantum realm. We try to form mental pictures, to make analogies. But these often fall short, or even mislead. The mathematics of quantum mechanics is precise. It makes stunningly accurate predictions, but the meaning behind the maths remains elusive. This gap between mathematical description and intuitive understanding is a source of ongoing debate, and for some, a source of anguish. Richard Feynman famously said, "I think I can safely say that nobody understands quantum mechanics." The baffling nature of quantum mechanics has led to a century of debate. There is no single, universally accepted interpretation of what it all means. Different schools of thought offer different pictures of reality. The Copenhagen interpretation, developed by Bohr and Heisenberg, is perhaps the most traditional. It suggests we should not ask what quantum systems are when unobserved. We should only focus on the results of measurements. Reality, in this view, is what we measure. Then, there is the many worlds interpretation, proposed by Hugh Everett. This interpretation takes superposition to its logical extreme. It suggests that every time a quantum measurement is made, the universe splits. All possible outcomes occur, each in a separate parallel universe. So, Schrödinger's cat is both alive and dead, but in different branches of reality. This is a mind-boggling idea. It populates reality with an infinite number of unseen worlds. Yet some physicists find it an elegant solution. Other interpretations exist. Bohmian mechanics, or pilot wave theory, posits hidden variables. It suggests particles do have definite positions, guided by a quantum wave. This restores a degree of determinism. We try to understand quantum physics using analogies. We compare superposition to a spinning coin. We liken entanglement to a pair of gloves. These analogies can be helpful starting points. They give us a small foothold in an alien landscape, but they are ultimately limited. They are drawn from our macroscopic world, the world of definite objects and classical logic. The quantum world does not play by these rules, and so, our analogies inevitably break down. The quantum world is not just a smaller version of our world, it is qualitatively different. Particles are not tiny billiard balls, they are also waves. They are clouds of probability. They can be in multiple places at once. No everyday object behaves this way. A football is either here or there. It cannot be both. A wave in the sea spreads out, but it is still a single wave. A quantum particle is somehow both particle-like and wave-like, and something more besides. The difficulty arises because our language itself is classical. The strangeness of quantum physics is not just a scientific curiosity, it can provoke a kind of existential dread. It challenges our most fundamental assumptions about reality, and about our place within it. If reality is probabilistic, what happens to free will? If observation changes the observed, what is truly objective? If distant particles can be instantly connected, what does separation even mean? These are not just physics questions, they are philosophical questions. They touch the core of our being. The idea that the world is not as solid and predictable as it seems can be deeply unsettling. We like to believe in a stable reality, a world that behaves according to clear, understandable rules. Quantum mechanics pulls the rug out from under this belief. It suggests a reality that is fluid, uncertain, and perhaps even illusory in some ways. This can lead to a feeling of groundlessness, a sense that the foundations of our world are not as firm as we thought. This is the fear. The quantum mystery scientists fear. Moreover, the implications for our sense of self can be disturbing. If the observer is entangled with the observed, where do I end and the world begin? Despite the unsettling nature of quantum physics, the quest to understand it must continue. It is not merely an academic pursuit, it is fundamental to our progress. The technologies of the 21st century are increasingly built upon quantum principles. Quantum computing, quantum cryptography, new materials, advanced medical imaging. These are not distant dreams, they are emerging realities. And they all depend on our ability to harness the strange rules of the quantum world. Beyond technology, there is the sheer human drive to understand. We are curious creatures. We look at the stars and wonder. We look at the atom and wonder. To turn away from the quantum mystery because it is difficult or unsettling would be to betray this fundamental aspect of our nature. The universe is offering us clues. Clues to its deepest secrets. It is our privilege, and perhaps our responsibility, to try and decipher them. Even if the answers challenge our most cherished beliefs, the fear and the bafflement are part of the process. Every great scientific revolution has been met with resistance, with a sense of disorientation. Copernicus showed us we are not the center of the universe. Darwin showed us our kinship with all life. Quantum mechanics is showing us that reality itself is far stranger and more subtle than we ever conceived. Each of these shifts was initially unsettling, but each ultimately led to a richer, more profound understanding of our world.